Hi everyone, thanks for coming tonight. I'd like to first begin the event by acknowledging that the land on which we gather tonight is the traditional, ancestral, and unceded territory of the Musqueam people. Yeah, and I'm pleased to introduce today's speaker, Joseph, who I've had a pleasure to know for some time at the college, probably since the middle of the pandemic. Joseph is multidisciplinary scientist whose backgrounds include classics, chemistry, material science, and archaeology. Today, Joseph will talk about shapes, how drawing shapes can be an exercise of inquiry, but at the same time, an exercise of power in science based on his multidisciplinary career. Without further ado, I'll leave the floor to Joseph.
All right, I think my mic's live. Thanks everyone for coming. As you probably saw from the abstract, I did myself no favors in picking a topic that's pretty big. I'm going to be talking tonight about things that I've done throughout the last decade, basically. This is too big to fit in a talk like this, so I'm not really going to try. And I ask that you be patient with me if my slides sometimes have slightly different formatting or my citations are different or things like that. I'm excited to share with you some things that I've been interested in for a long time and some ways that I've kind of jumped between worlds as an academic and as a researcher during my career. Okay, so without further ado, let's start where we should. The good Calvin and Hobbes comic. This is an early one. Show of hands, who here has read any Calvin and Hobbes or recognizes this? Okay, cool. All right, great. There's a lot of folks here who've seen this before. For those of you who haven't, this is a cartoon that ran in newspapers in the United States and elsewhere during the mid to late 80s and early to mid 90s. This is one of the earlier ones, and this comic strip is about Calvin, a young, precocious, and also very dumb child who has a best friend who's a tiger named Hobbes. If you're paying attention, you might notice that Hobbes, as he appears throughout this comic, is a little bit different from how he appears in this last panel. There might be a reason for that. Is he real? Is he not? This is one of the things that this comic likes to play with. Sometimes Calvin's imagination around Hobbes gets him into trouble. This is another good one. This is a central trope of this comic, is that Hobbes likes pouncing on Calvin because he's a tiger, and that's what tigers do. These are pretty straightforward comics, but here's the same kind of trope again. But let's pay a little bit more attention to the layout. Let's see how this is, how Bill Watterson is playing with the layout a bit here. It's still blocky, rectangular, square panels, but now there's a sense of timing to it. Some of the panels are wider. Some of them, they like to play with juxtaposition in terms of facing, so you can see that Calvin's facing one direction in this one, and Hobbes is facing the other one. You can start to get a sense of opposition. And then there's the subtle, but I think still quite smart layout of the last couple panels where the final panel is sitting in front of the door. It's the door to Calvin's bedroom. And so it's like you're entering that bedroom when you go in this last panel. As time goes on, as time went on, Watterson got more and more creative with the way that he laid out his comic. This is from several years later. And this is one of my favorite examples of the ways that he did this. How many of you have seen a comic like this before in a newspaper? They don't make them like that anymore. And they didn't then either. This is something very special. And it inspired a lot of people, both cartoonists and otherwise. And the sense of motion that this carries with the way that the shapes are laid out is just absolutely amazing. It's like you're watching a movie, but it's just still images on a page. Here's another example of that, but this brings us into another really key aspect to this comic, which is A really important part of Calvin's character is his very rich internal worlds. One of the things that he likes to play as is Spaceman Spiff, which is the spaceman you see in this strip here, crash landing on various worlds and getting himself out of all sorts of trouble that he had nothing to do with, nothing at all, really. And this plays out in various ways in Calvin's daily life, such as when he's in the bath. And here you can see another perspective on that trope, one that I think is rather more poignant and that I quite like. Now, I'm talking about a newspaper comic. I didn't mention that in my abstract. And I've talked a bit about the layout of these comics, and that's kind of shape-related. But let's pay a little bit more attention to what's actually shown in the comic itself. I really love this comic specifically because of that space scene in that final panel, if you could even call it a panel. It's more of like a splash or something. The way that Watterson plays with lines and colors and vastness of space, if I go back one slide, you can see it, especially in that opening splash as well. I loved that as a kid, and I still do. He's not necessarily drawing directly from this next person I'm about to show you, but he's certainly drawing in the same artistic environment as this other person drew. This is a splash from, or this is a panel from a, I think you would object to being called a cartoonist, an artist named, that went by the pen name Mobius. And he drew some of the most famous and highly acclaimed comics of the 1900s. Whole sections of his work were lifted into movies like Star Wars and various adaptations of Dune. If anyone here has read Dune, the kind of like psychedelic, weird neo-spiritual kind of Eastern but not kind of stuff that Frank Herbert really just bathes in, this is similar to some of the stuff that Mobius really exudes in his world building. So here we see a panel of two people on top of an asteroid that they just crash landed on a planet, because it's also a ship. And this asteroid, these two people are named Stel and Atan. And they crash land on this planet, and they see a star-looking thing in the distance. And they find a vintage car in their asteroid, and they start driving towards it. And as they get closer, they eventually find that light is coming from a big old space pyramid. And it's a space pyramid that's surrounded by a city, and there's all these people that are like congregated around to see this space pyramid. They're like, what is this? What does this do? And this is Stel, who seems to be called up to this space pyramid. I love the way that this panel looks here. You got this empty space with just flecks of stuff, and you've got these impeccably clean lines. That's one of my favorite things about Mobius's art is his lines. And you can really see it in this one, where Stel goes inside the pyramid and sees a number of beautiful things. And shortly thereafter, the following day, the pyramid starts sucking up all these people, and they go off to intergalactic version of Eden, which is why this book is called The World of Edina. If you add an A onto it, it's original. So as I was saying, there's a number of things I love about Mobius's art, but two of the biggest things are the way his line work just uses empty space to create this huge sense of clarity and gravitas, but also the way he draws really intricate details within and around that empty space to magnify that feeling of weight and to make it actually move. And I think that's, in some ways, best emphasized in that panel on the right, that last one. Personally, I think both of these can also be found in the work of someone very different. These are cartoons from my favorite New Yorker cartoonist named Saul Steinberg, who is unfortunately no longer with us, from Romania. And these are some of my favorite of his, where he's conveying these intricate details, the harp, these beautiful textures with a paintbrush of different kinds of instruments. His art really defied categorization in a lot of ways, but mostly I just love the way he drew lines. So let's do some lines of a different sort. This is methane. How's that for a segue? This is an organic molecule, organic meaning that it contains carbon, and we're going to talk about molecules now. So methane is carbon and 4 hydrogens. And I recognize that many of you, if not most of you, if not all of you, probably last thought about Lewis structures a decade ago. So we're going to think about them again. This here on the right, you could call a Lewis structure. The name isn't important. The important thing is we're going to talk about how we draw molecules, or specifically how organic chemists draw molecules and how they think about them in 3D space. So what that thing on the right means is better represented by what the thing on the left shows. And what the thing on the left is supposed to show, even though it's a flat image, is it's supposed to show a 3D shape. A wedge that's black indicates something coming out of the board, and a dashed line indicates something going in. How many of you like visual reasoning? Cool, great, we're among friends. For those of you who are not and have trouble visualizing this, you can imagine this thing is just like a pane or a sheet of paper, and you can see that the dashed line is behind it. So when we're thinking about how we draw molecules, the main takeaways from this slide are basically the rules of the game are every atom has to have a certain number of bonds for it to be okay. Carbon has to have 4, nitrogen has to have 3, oxygen 2, etc. This is a lie in a sense, but you don't need to worry about that. Atoms, the second thing is that atoms around a central atom will push each other away. And so the farthest that the hydrogens can get away from each other are indicated by the structure on the left there. This is ethane. We can call this way of drawing in the middle a wireframe diagram or a wireframe drawing. And we can call the thing on the left a dashed or dashed wedged kind of drawing. Now, organic chemists are lazy, as many chemists are, as many scientists are. And so the way they would draw this is they would just draw a line. And this line just indicates every point on this, every point or endpoint or vertex of this line is a carbon. And whenever they don't say what else is attached to that carbon, you should assume it's hydrogen. No big deal, right? Easy peasy, says the chemist. The way this would look if you had something that wasn't a hydrogen, say ethanol, this is ethanol, CH3, CH2OH. You can see on the dashed wedged over there that should make pretty good sense. And then on the right, that would look like that. So you got an oxygen and hydrogen knocked onto one of those carbons. Okay, so like that's kind of the way that people tend to draw things. So let's think about that wireframe drawing again. Let's replace some of those hydrogens with other things. So if we were to draw this in a wedged, dashed diagram sort of way, we could do it by, you could imagine in your mind's eye that this hydrogen right here is the one that's pointing up on the wedge dash, and then this one, let's say, is the one that's pointing out because it's pointing towards you a little bit, and then let's say this one's in the plane of the page, or maybe this one, let's say bromine's in the plane of the page, and F is pointing in. So it's easy for me to like just imagine that in my head because I've taught this to a lot of people. This is one of my favorite things to teach in organic chemistry, is looking at a two-dimensional image and seeing something in 3D. And so what you see on the left here is what I was just talking about, where you have, not that yet, where you have the chlorine coming out of the page, the fluorine going into the page. But if I were to switch the position of the chlorine and bromine in the middle diagram, that doesn't change anything about how the wedge dash thing has to be drawn. They're all bonded to the same thing still. But if I switch them, that's then, following the same procedure I just followed, what you would come up with. And if you're observant, or if you're skilled in visual reasoning, you would maybe be able to see that there's no way to superimpose those two molecules on top of each other. They're different. This is perhaps even less visible since you're all in the third row, which is a better viewing angle, I will own that. But if you can see these, they don't superimpose. There is no way to rotate this thing around so that it exactly matches up with this. And that means they're different. They're clearly two different things. You can't rotate one and turn it into the other. There's something fundamentally different about those two things. And this problem, or opportunity, is what chemists refer to as stereochemistry. And we call these two things enantiomers. Now, these two molecules behave very similarly. The lethal dose is pretty similar. The boiling point is the same. You could come up with all kinds of specs that are similar. But they're different. They manipulate light differently, and they'll interact with your body slightly differently as well. I was going to teach you how to do this yourself, but since we're already 15 minutes in, I'm going to skip that, and if you have questions about that, we can go over that later. But suffice it to say that the one on the left is called R-bromochlorofluoromethane, because you have to use your right hand to make it do the thing when you're figuring it out. And the one on the right here is called S for sinister, which is Latin for left, because you have to use your left hand to do it. So this is pretty important. This is so important, in fact, that these two molecules I'm showing here represent different odors. They both bind to olfactory receptors in your sinuses, and they smell different. Y'all can pass these around. These are them. This one, in this big bag, no, I'm not going to remember it until I flip the slide up. But that's caraway seeds, and this is wintergreen. These are two very different plants. Spearmint, sorry. Spearmint. Two very different plants, completely unrelated, or almost completely. And both of them produce a lot of these two molecules, which are very similar to each other. The one on the left is the smell of caraway, and the one on the right is the smell of spearmint, and these are called carvones. This is a more complicated looking molecule, or set of molecules. This is another indication of how important this is. The one on the left is naproxen, which you might have heard of, very common NSAID. The one on the right is a very potent liver toxin. There's one carbon different. And the ways that chemists think about making these kinds of molecules requires that they be able to do a lot of gymnastics on paper using their head for an aid. So I don't have time to go through it exactly, but this is one of the main pathways for synthesizing naproxen. And if you were faced with this problem in a classroom setting, what you would have to do is you would have to draw where the electrons from the different reagents that you're adding, reagents are above the arrows, what they attack. So this one would what's going on here? So the bromine would attack the carbons here and here, and you'd have to show how you can complex it with magnesium then to prime this bromine for attack, and then this reagent here would attack it, and so on and so forth. And then one of the ways that chemists monitor reactions like this is they do something called infrared spectroscopy. This is a spectrum right here. And one of my favorite ways to kind of explain this to people is this is a way of showing what wavelengths of light produce the most wiggles in the molecule. This is not wiggle matching. That's something in dendrochronology. But you can think about it a similar way. That's all I have for a segue into another kind of wiggle, which is the wiggle that electrons do in nanoparticles when you shine light on them. So light's an oscillating electromagnetic wave, and so when you put charged particles in an oscillating field and you confine those charged particles to a shape, such as this nanoparticle here, they'll start to oscillate back and forth. And depending on that shape, different wavelengths of light will produce different kinds of oscillations. And the most coherent of these we call plasmon resonances. And these plasmons allow the particle to absorb energy, and that causes the particle, in a sense, to absorb light. And when that happens, you get different absorbances and transmittances, and this creates color, either in the visible spectrum, in the case here, where you have different gold nanoparticles and rods creating different colors in solution, or elsewhere in the electromagnetic spectrum. And this is something that people have used for thousands of years, actually. This is a very pretty looking cup called the Lycurgus cup. It's quite famous. It's in the British Museum. And the color in it that you see actually comes from gold, silver, alloyed nanoparticles. This is what it looks like when there's no light shining from inside or behind it. And you can see that it looks very different. And this is one of those particles. And then there's other examples of this, including the Avila Cathedral in Spain. Some of its windows are colored using silver nanoparticles. Probably going to skip over this analogy here, but you can think about this kind of like being in a car on a rumble strip, and the car starts vibrating because of the rumble strip, and then you perceive that rumbling as a stimulus. That's the same idea as having a nanoparticle vibrating with light that you perceive as color. We can look at a very nice looking animation that I made using the simulation software that I'm got most of the data that I'm going to use from. So the resonance that I was just talking about changes, the wavelength that produces that resonance changes depending on the particle's size, shape, and composition. So if you make it bigger, the resonance will shift to a longer wavelength of light. And if you change the composition, it changes everything because it changes the dielectric properties of the medium. So we can turn one of these spectra into a visible color using a process that I'm going to talk a little bit about I'm not going to talk about the actual math. You can ask me about it afterwards if you like. But you can think about this as analogous to taking three colors, like RGB or red, yellow, blue, or cyan, magenta, yellow, key, as your printer uses. And we have something called color matching functions, which we can use to determine, to describe what parts of the spectrum are most, trigger the stimulus that our eyes perceive as a certain color. So this is for red, green, and blue. And if you do some linear algebra and you add up all the area under the curve and you multiply by the weights given in the color matching function, you arrive at a value. You scale that value from 0 to 255, which is like what Microsoft Word allows you to do, and you come up with a number, 231. You can do the same thing for the green color matching function, for the blue color matching function, and then the color that you get in the middle is what happens when you add them all together, and it's a pink. And this is what we expected if you think about the Lycurgus cup, and it's pink. There you go. On a less flippant note, we did this and then compared it to experimental results. So we tried to simulate the colors that we would expect from rods that this group did experiments on over on the left. And the colors that we produced from the spectra that we got over on the right are pretty comparable, especially considering that we were trying to normalize to different concentrations and things like that. So since I was saying that we did simulations on this, when you have a simulation framework you can work within, it becomes very easy to sweep over a bunch of different parameters. So we wanted to use this to investigate what other colors you could make with gold and silver nanoparticles. So we could vary the material between gold and silver. We could vary the background material between water and glass and all kinds of other different dielectric media. And then we could change the size of the rods or the spheres by varying the radius and length. I I'm happy to tell you about orientation and light polarization later if you want, but we'll leave it out of this for right now. Those of you who were here 3 years ago when I last talked about ancient artisanal nanoscience will maybe remember the next slide. These were the colors we got out. So these are some of the coolest looking figures that I've ever made. And these basically these are plots that show what radius and length of a rod of a certain material in a certain medium would produce visually, what color. And so you can see that the gold over on the left, I doubt you can see that's gold because the labels are small. The plots over on the left, this is for water and this is for glass. You can see the colors are kind of very similar to what we saw, the range that we saw in the Lycurgus cup with these peach and pink and getting down into purple as you get bigger and the wavelength shifts. And then with silver, you can see some of the reds and yellows that we'd seen. Many of the particles that were used in those windows that I showed you are close to spherical. But we also got some colors we didn't really expect to see, these blues and pinks. I think I've seen those in one artist that's used those before, but certainly not in any historical sense. And then we turned this data set into a science museum exhibit. And we developed an application that you can view online to help learn about nanoparticle-based coloration. That's far from the only application of this sort of thing, though. I don't have a lot of time to talk about it, but broadly speaking, applications for these kinds of plasmonic nanoparticles range from different kinds of photothermal therapeutics. There are people who use very directed radiation and nanoparticle injection into tumors to cook the tumors, believe it or not, which is one way, a very effective way of killing them, depending on the diagnosis. You can use them to help with steam generation, and one of the biggest applications for these is in biological and chemical sensing, because it turns out that measuring the shift in a particular spectrum is a very precise way to detect that the environment around a particle has changed, and you can get down to detection limits that are in the single particle or single molecule kind of sense. And then something that I'm going to touch on very briefly is you can use these to enhance different kinds of spectroscopy, especially Raman spectroscopy, by using the when the electrons scatter to the ends of the nanoparticle, you can use those regions of high charge density to really enhance and amplify the signals coming out of the spectrometer. So this is an example of one of the particles that we investigated. This is a pentatwin rod with various dimensions that you don't really need to know. They just look cool. And this is an example of one of the figures we used in our publication, where the stuff over on the right here is basically showing you where the regions of high charge density are. And you can see how, for one interesting thing, for example, is that in the top right image up there, the regions of charge density up top are smaller than the ones down below. There's reasons for that. This is also not exactly charge density. It's E-field enhancement, which is the magnitude of the electric field raised to the power of 4. But yeah, these ways of visualizing with colors around the modeled shapes was a novel part of our paper that we're quite proud of. Yeah, I don't have a good segue after that, but somewhat of a similar sense. So we were just talking about how particles that are charged, that are confined to a shape, behave differently under stimulus, and that the ways that they behave can tell you information both like about the nature of the shape itself, but can also produce new questions, new ways of looking at that information that you can ask about. And a somewhat analogous way somewhat analogous to that is thinking about architecture. And this is what I first came to UBC with what I was thinking about in my head of doing research on. And so there's this term space syntax refers to basically a collection of theories and methods that really were first pioneered by people named Hillier and Hansen. You can see down there, this quote is from them. And they wanted to basically look at a building's topology and to some extent its geography, so its connectivity, and to some extent its, where different rooms are located, what their dimensions are, to investigate their ideas around material agency and how that factored into spatiality in philosophy. But their techniques tend to be very practical, very practically minded, and a set of them is called access analysis or convex space analysis, and this is a way of basically taking a floor plan and thinking about the ways that rooms, which you can think of as convex spaces, connect to each other. And you can do this, if you follow their example, by making something called a justified access graph, which just has nodes that are rooms or convex shapes connected together with edges that represent doorways or other sorts of connection. And potentially with an axial map as well, which just tries to determine the smallest number of shortest pathways through a building that pass through every space. And this body of techniques is useful for a number of reasons, but one of the reasons I was interested in using it is that it's particularly attractive to people who only have floor plans. Let's say they're trying to get new information out of old data in a situation where they can't go and collect new data, or there are problems with the way that the data was collected originally to begin with. And this is the case for a site in modern-day Syria called Ugarit, which is a fun name for a city. This is a Bronze Age city on the Tell of Ras Shamra. It was settled a long time ago. There was a period of abandonment at one point, but it rose after that to a position of high prominence in the mercantile world of the late Bronze Age. This was one of the big powers in terms of trade with regions far and wide across the Near East. There's some Neolithic remains. It was primarily excavated to begin with by this person named Claude Schaefer. You can see he was there for a long time. There were problems with the way that Claude Schaefer excavated this place. The plans that his team produced are very schematic. Many of the drawings that they made weren't actually published. The ones that were, the fine spots in the scans they used were, you couldn't read them. Sometimes they were misaligned. Sometimes they weren't recorded at all. He wasn't a dynamite archaeologist, but there were problems with the way that he did things. And Ugarit, you can see here is a map of the range of some of the different merchants that we know of who lived there. This is a small town. I mean, it's an important power, but if I go back to this map, you can see that this scale here is in meters, I think. It's not the biggest place. And it still had a massive range. So this is Cyprus right here. The Tigris and Euphrates, this is this region, this is Mesopotamia. And these are where merchants are going. And they're talking to heads of state. These are important people. And we know about this because we have their tablets, or some of them. And they talk about it. And this has prompted a lot of scholars to ask questions around how much trade was state-driven, how much was private, if this sounds capitalist, or a capitalist kind of question. It's because it is. And the fragmentary nature of the archaeological remains of this site has interacted with this kind of dichotomy, this false, in my opinion, false dichotomy, by producing diagrams that look like this on the right. And this is purporting to reconstruct some of the economic structures and systems at play in this city. And I didn't like that. because I look at a thing like that and I'm like, where are the people at? And part of this is because I'm not an economist. I don't look at things like that and think about people. And some people can do that. But I think there's something that's lost in looking at, in just trying to reconstruct the economics of a place in this way. And so I wanted to think about what spaces can tell us about the nature of exchange, especially since these sorts of long distance trade networks are really logistically intensive, and that requires really efficient record keeping and a stable base of operations. And so in the project that I'm talking about, I basically did justified access graph analysis and some other kinds of spatial analyses on these three structures. I don't have time to talk about all of them, so I don't have time to compare them to you, but I'll talk a little bit about the one in the middle, which is the house of Yabninu, a merchant, perhaps one of the most important ones. His house was right next to the palace. There's literally right next to the palace, just across a small street. And his house is much bigger than many of the houses that are attested. And so in these figures that I'm showing here, which are helpfully color-coded differently because me of fall of 2020 was dumb, you can see the different rooms in the first floor of the house over on the right. There was originally a second floor. I'm not sure if there was originally a third. I don't even know if we can actually know that. But we have the complete floor plan from the first floor, and we know where tablets were found, and we know what were courtyards, what were roofed and unroofed because the second floor collapsed. And then on the left, I've turned this into a justified access graph with color coding showing different kinds of spaces. And there's a lot of ways that this can be used. A lot of the conclusions that I drew from these are in comparison to the other structures. But some things that I do want to point out that are a little bit difficult to get from the floor plan. Well, where we go? Where did my mouse go? There we go. They're a little bit difficult to get from the floor plan, but I think are easier to see from the access graph. So the brown circles here are tombs, and those are among the least accessible rooms in the entire building, often requiring you to go make multiple turns to get to them and access them from small spaces. Tablets, which are found in these rooms here, highlighted in red here, are about 3 or more spaces away from the entrance. And the interesting thing about this is that in the palace, they're generally found much closer to the entrances. And these were probably stored on an upper floor, probably. Given the state of the publication, it's hard to say for sure. But that says something about the way that tablets were stored here as opposed to in a royal residence. And you can also draw other conclusions from this about the function of courtyards in linking circuits together throughout the house. And you can see that there's 2 main circuits, one here, one here. You can probably already see that from the floor plan. So there's one right here and one right here. But this emphasizes how courtyards are really used to link both as a linking function and as a hub function. So this one is functioning as a hub, and this one is functioning as a linkage in ways that can be a little bit more difficult to see, I think, on a floor plan. There's other ways this can be used, but this is the one that I had time to talk about here. You may wonder, in looking at this, why are we taking a collection of black rectangles and turning them into a graph? This place was butchered from an academic perspective in some ways. It's part of a war zone. The Tel of Rosh Shamra is home to a Syrian state military base now, which is partially built over these ruins. Is there something wrong with stitching this place up and making it dance on a graph like this? I think that's a very good question. It's something I think about. And it does prompt us to talk a little bit about where archaeology came from and where some of these problems came from. Western archaeology mostly grew out of antiquarianism in the 1600s, which was mostly just rich Europeans who'd grown up learning Latin and Greek, going places they'd read about in school, and hiring poor people to dig for buried treasure. That's what it was at the beginning. These were amateurs in the original sense of the word. They revered Greco-Roman art and architecture really as aesthetic ideals. And above all else, they sought to collect inscriptions, pottery, jewelry, sculptures. And the motivation for this was that it was more than just admiration, really. It was entitlement. This was taking place in the shadow of the Renaissance in Europe, and most of these people had deeply internalized the idea that they were the successors, the heirs to the Romans and the Greeks. Obviously, this is racist. This is incredibly racist. It's also wrong, but it's racist. This was part of their idolization of white, muscled European statuary that they mistook for bodies. These statues would originally have been painted. Nobody cares in the 1600s. And based on their collections of pottery and culture, they really came to believe that Roman and Greek societies went from primitive beginnings to unsurpassed technological peaks. They established a chronology, a system of growth and decline. And the key piece here is that these beliefs were really not historical. Sculptures were generally colorful, as were buildings. And Romans didn't think of themselves as a monolithic culture in the way that modern people tend to say they did. It's not that they didn't necessarily, it's that the notion of culture and the notion of monolithic are very different, and they work very differently in the ancient world. So the way that these people retrojected their own ideas about value and culture onto the ancient past really has major implications for how archaeology develops. And the philosophical, so in the 1800s, archaeological research kind of got twin injections of scientific authority and nationalistic urgency. So as it became increasingly professionalized from an institutional standpoint, this is around the same time that race science is really starting to become a thing. Eugenics, statistics, some of the parts of early physical anthropology, this is kind of a bubbling cauldron of things. And the philosophical impact of this is obvious because it's just a small jump. If you already believed that the Roman and Greek societies were aesthetically and technologically superior to others, now you believe that their superiority was rooted in biology. And of course, if some societies can be biologically superior to others, what does that mean about your society? This is one of the sentiments that undergirds some of the first attempts at archaeological theory, where people try to translate this artistic hierarchy of development and decline into societal hierarchy and decline. This is where we get the ideas about Stone Age, Bronze Age, things like that. So you can see where this is going from a nationalistic standpoint. It becomes increasingly important to prove you are the heirs to the Romans. And there's a lot of wars and things that should have been wars or shouldn't have been wars about this. This is one of the innovations of the 1800s, which is some instruments that were used in craniometry, which you probably first learned about in relation to Nazis and eugenicists. And this is people writing more similar stuff. So the way that I wanted to use this background or engage with this background during my time as a student here was to look at a site called the Birsa Hill. The Birsa Hill is a site in Carthage. That's where Carthage is. It's in modern-day Tunisia. You might be surprised to notice, if you're not familiar with this part of the world, that it's actually west of Rome, I think. And it's very close to Sicily and Rome and all of these places. This area right here, this, what is that called, the Tyrrhenian Sea? I don't remember. I'm a bad classicist. Is super important in the from like 500 to around the turn of the millennium. It's very important in other time periods too, but especially during the rise of the Roman Empire, the rise of the Roman state, and eventually the rise of the Roman Empire. Because Carthage was Rome's main geopolitical rival. And they were eventually, after a series of wars, crushed in 146 BC when Rome sacked their city, enslaved all of their people, and razed their structures to the ground. 100 years later, they came back and they founded one of their first imperial colonies there on the bones of the ruined city. And I'm not going to talk a lot about the history of that because I'm going to focus on other things, and we're running out of time a little bit. The site of ancient Carthage has a long and complicated history after the Romans. It goes through occupation by various Byzantine, Vandal, Islamic groups, and then it's complicated further in the 1800s when the French arrive and colonize Tunisia. The excavation history of the site is also complicated. These are most of them. I want to especially point out there's a woman here, Burkhart, from 1947. She had one publication, but boy howdy, it was a good one. Most of the people from the top row never published together, even though they were working within 5 to 10 years of each other. And the same is in some ways true of the bottom row, even though they were all under the auspices of the same archaeological mission. This produced a number of problems. Problems of consistency. So in this map here, this wall that's shown highlighted in red isn't in the other map that they published, or one of the other maps that they published this area. You can see there's part of it, and then it stops. A lot of the maps exclude, especially the historical ones, exclude features that were from similar people. So in this map on the left, this is Delattre in 1893, completely omitting things that someone was writing about 20 or 30 years before, right over here. And then his things, his walls, he would call them his, which are supposed to be right around here, are omitted 40 years later in someone else in the works of someone else who we know saw them, but he didn't think it was worth including in his map. And then there's problems of attribution. So things you see in one map, so this is from 1983, claiming to be an original figure, credited to Robin. This is the same map. It's published in 1990 by a different author. Doesn't attribute anything else. He just says after the plans of Robin. This is from 2020, and it claims to reproduce the 1990 map, but you might notice that they're different. All the stuff around here, no, maybe. All the stuff around here is missing, or is present in the 2020 map, but is missing in 1990. And actually what this map is reproducing is this one, which is published in 2011, except without the grid over the top of it. They're all definitely derivative of one another, sort of, but how? Which one's right? And in some ways, all of them are kind of wrong, but I can't really talk about that. I just realized because I don't have time. Because there's things that they're omitting that did exist and still exist. It makes you wonder what dotted lines mean. I don't really have time to talk about the different, the design of the intricacies of the system I designed to kind of like untangle this mess. But I can show you a diagram of it, which is basically I came up with a data system that had like geospatial features, like shapes on a map, linked with different kinds of metadata that could ground what I drew on a map in a specific figure that someone else had published, and that could record what assumptions I made in drawing that feature. Because a lot of those maps that we saw before clearly had assumptions in them. Does a wall exist or not? And there was no way of telling what they had assumed. And this is a section of what I produced with that. And like I said, I don't have enough time to really go through exactly how this works, but basically, this is an illustration of it, where a feature has a source field that identifies maps that it's from, and assumptions. So this is a shorthand for an assumption, axis 22. And axis 22 is got a description that tells you exactly what the assumption is, and is also linked to specific maps, these ones. And finally, it tells you what sort of features it's linked to, right there. Yeah, so that's how that system works. Recent work that I've been doing, I don't have time to talk about it right now, but since I finished my thesis, I've been doing a lot of programming in QGIS, which is the mapping software I used, and I've developed some tools I'd love to tell you about another time. And so with that, I'll end with the last Calvin and Hobbes comic, which I think is a good, hopeful note to go out on. There's a lot of blank space out there to draw things in and explore, and that's a good thing. And with that, I'll take questions.
If you have
Pedro.
Hi, thank you for the presentation. I have a quick question. When you show the RGB plot, you said we have 2055 choices for each color.
Yes, so let me go back.
Which sounds like just a byte restriction for 2 to the 8.
I'm just going to go back to this slide, especially for the people watching on stream. So could you repeat it one more time?
Yeah, so you were talking about like how the when you create these RGB plots, you have a restriction in each of the colors of 255 or 256, which just sound like, oh, like it's just the size of the byte, like you're trying to represent each color by a byte. Do you have, does that introduce, could we go, if we allow it to go to 2 to the 9, for example, could we have like new colors? Or will just be like more resolution in the colors? And
So this is a good question. So there's this whole field out there of color science that is very interesting. This is one of the most interesting applications for linear algebra that I know of. And so there are different color spaces that companies have created and patented that have different ways of achieving resolution and also diversity of color options available. You're right that the number 255, 0 to 255, is certainly related to the way that computers store information in bytes. It's a very handy way of doing that in an integer form. The reality is that when you go through, so if I go and point out the thing that I said I wasn't going to talk about, tri-stimulus values x, y, and z are kind of like a middleman between different, a way to convert between different kinds of color space. And those are scaled from 0 to 1. And of course, they're decimals. So they can be, you can make them as precise as you like. But depending on the color space, the conversion will, chop off some of that. Yeah. Yeah, another question.
Hi, thank you so much. This is so interesting. I was really interested in the work that you did, I guess, with your thesis and the way that you explain kind of what the questions that you were, that kind of brought you to then do what you did. And I guess I'm kind of wondering what you feel that the implications are for drawing shapes, for relating to shapes differently for archaeology, given the background that you were kind of trying to bring into contention with your work. Like, how do you, I guess my question is, for someone who maybe doesn't necessarily work with, I guess, but is really interested in what are you trying to, because I think even when it came to the molecules and everything, it's something about trying to challenge the fact that the ways in which you represent something spatially actually has a lot of meaning, and those differences are kind of lost when you try to apply it to the 2D, I guess I'm understanding. So I guess like what does the mapping and the accounting for assumptions, like what are you trying to like account for and how archaeology has been working to get at what you're bringing into contention?
I will do my best to offer a coherent response because it's 9 p.m. The first thing I have to say is like, I think drawing is fun, and I think making shapes is fun. That's why I did this, all of it. But as you were pointing out, and as I was pointing out, as soon as you cross the road as soon as you cross the line into drawing shapes about people, that's where it gets dangerous. And I think I was thinking about this earlier. I think a good way of summing up of like providing a very succinct view on this is I think a lot of what goes wrong in archaeology is when researchers miss people for the shapes, because it's about people. The forest for the trees, people for the shapes. And it's a very seductive thing to like, oh, I drew this, it's real. Like, as soon as there's a sense of power in holding a map and you're like, wow, this is what it was. Or even, maybe if it's not like that, wow, someone cared enough to draw it. And so I think when it comes to making maps, it's important to be very careful, as any map maker would tell you, but it's also important to have a robust system in place to check that it is right and to check that it is motivated well. This is straying a little bit from your original question, but one of the things that I really argued a lot about in my thesis was that part of what was so wrong with the maps that I was working with, stuck in my bedroom during COVID, was not just that they were wrong, but that the things that were wrong were obvious, and people had missed them for 50, 60, 70 years. You know, people had known there's issues with the stuff from the 30s or from the 1800s for a long time. But I wasn't finding anyone that was critiquing the maps that were published under the French mission in the 50s and 70s and 80s. And that's a real big problem. And that has a lot to do with the way that publication works and the way that peer review works when you're publishing monographs in archaeology. So I have a lot of ideas about how we can go about fixing that, but that gets pretty far away from your question. Thank you. It's a great question.
Yeah, any other questions? I think we can take one last question.
Hi.
Hey.
One last thing, maybe. I think it was more about when you started showing the shapes of, I think it was of the chiral compounds.
Mm-hmm.
So if I have, how do they go from one? Is it easy chemically to go from one to another? Like to go from one that has carbon, chlor in one to go to carbon, chlorine on the other one?
So are you talking about
like a bit
no,
next?
not that far. So are you talking about like the initial one?
Like, or the previous one. Is it easy to change? Because here it seems trivial to do, but is it easy to do do you have a
No, it's not easy.
Okay.
This is a great example, actually, because I think this particular compound, bromochlorofluoromethane, is actually very difficult to isolate them. So when you synthesize this, you'll get a 50-50 mix, especially with this one because it's so simple. And this is actually a molecule that people use to study like parity breaking behavior, like still today. I think it was only in 2011 that someone managed to synthesize one stereospecifically. And people have known about this for well over 100 years. It can be quite challenging. If I go forward to the naproxen synthesis that I showed later, the point at which there is no there are no enantiomers possible until this step right here, where you add magnesium and then you have the, whatever this is, attack the carbon that has the bromine on it. And this is the point at which you have a racemic, what's called a racemic mixture, where you have 50-50 of both enantiomers, because this has no stereospecificity. The way that they get one, the way that they get the one they want, is they react it then with a chiral compound. This is N-alkyl glucamine, the gluc coming from glucose, and glucose is chiral. It's very chiral, and I couldn't tell you off the top of my head how this reaction goes, but that's how they get this thing. So usually, the way that you get a pure, enantiomerically pure, or stereochemically pure compound has to do with reacting it with another chiral compound. Usually, not always, but like often it's something that's chiral because a living thing made it. We didn't have a chance to talk about this, but like the way that proteins in your body, the way the building blocks of those amino acids, they all have the same handedness in every living thing on this planet. And so the chirality is very much inherent to the building blocks of life on Earth. And so that a lot of the chiral compounds you'll use to react with things will be biologically sourced.
Okay, thank you.
The really cool thing comes when you want to make chiral nanoparticles, which people at the lab that I used to work at are doing. But I didn't get a chance to work on this. So, yeah, thank you.
I think we'll wrap up here. Thank you, Joseph, for a wonderful presentation.